Virtually all things vibrate or oscillate at a characteristic frequency. If the vibrating object is driven at just the right frequency, it experiences the powerful effects of resonance. In order to demonstrate how a vibrating object responds to an outside driving force, an air-track glider and a variable frequency driver will be used. Two springs are attached to either side of the glider, with one spring leading to a rigid support and the other spring directly coupling the glider to the driver arm. With the driver initially turned off, the glider is displaced from its rest position. When the glider is released, it oscillates back and forth at its own characteristic frequency, or what is called its natural frequency. Next, the external driving force is applied. With the driving frequency initially set at a value much lower than the glider's natural frequency, the glider at first goes through a transient stage, wanting to vibrate at its own natural rate and resisting the driving force. However, it ultimately gives way and reluctantly vibrates at the frequency imposed upon it by the external force. Although the glider gives in, the amplitude of its oscillation remains small. If the driving frequency is increased, the glider becomes more responsive as its vibrations start to grow. At this point, it is observed that the glider moves in step or in phase with the driving arm. If the driving frequency is increased to a point where it just matches the natural frequency of the glider, the amplitude of oscillation becomes exceptionally large. The glider and external driver are now said to be in resonance. At resonance, there is maximum energy transfer from the driving source to the oscillator. If we compare the displacement of the driver arm to the displacement of the glider, it is seen that a relatively small force can be used to obtain a large amplitude vibration. Also note that at resonance, the motion of the driving force is not perfectly in sync with the motion of the glider. Instead, the driving force leads the glider by a fraction of a cycle. If the driving frequency is increased to a value slightly above the resonant frequency, the amplitude of vibration once again diminishes. Here it is observed that the driver arm and glider are completely out of sync as the two motions oppose one another. At frequencies significantly above the resonance frequency, the glider shows virtually no response to the driving force. A graph of oscillation amplitude versus driving frequency can be used to summarize these results. Note that the vibrational amplitude rises sharply as the driving frequency approaches the resonant frequency from either side. A system composed of a single oscillator has only one resonant frequency and one characteristic mode of vibration. However, if two gliders are coupled together, two resonant modes of vibration can be observed. At one particular frequency, the two gliders move in unison. At a second higher frequency, the two gliders move so as to oppose each other. If three gliders are coupled together, three different resonant modes of vibration come into being. In general, the number of independent modes of vibration will always equal the number of oscillators present in the system.